Oh, thank you very much. Thank you, Dr. Praise, for this very kind introduction and also for the invitation. And I'm really delighted and very happy to participate in this seminar. I would also like to thank our hosts from University of Nairobi and especially Dr. Jared. So thanks again, and it's a pleasure to see many friends among the participants. I have been looking at the names, so thank you very much for attending. So this talk, the greatest part of this talk, as a matter of fact, will be introductory talk to financial modeling, to modeling of financial markets. And so the greatest part of the talk will be based on works of other researchers rather than works of myself and my co-authors. And only towards the very end, we will see some of our more recent results. So I will start by, maybe I can, so I just wanted to advertise some of our activities at the University of Leeds, which are related to financial mathematics, stochastic processes, and stochastic analysis. So we have a number of seminars. So I understood from Dr. Jarrett that it's possible to do this advertisement here. So we have we run a number of seminars, one of which is that seminar in probability and financial mathematics, and you are free to join. It is enough just to send me an email and I will add you to our mailing list. In March, we organize a 2-day special event on stochastic processes and their friends that is not so very much on financial mathematics, but really on stochastic analysis and stochastic processes and maybe connections to PD theory, partial differential equations. And then we have that very regular workshop between our university, Leeds, Liverpool, and York. And for instance, the speaker in the next seminar session here in the seminar in the African mathematical seminar, Dr. Olivier is a regular participant also in this workshop. And in May, we organize a very big conference around financial mathematics and actuarial mathematics. And information about registration is coming soon. And of course, you're welcome to participate in all these events. And even if for some, there might be some fees for other participants, from African higher education institutions, that will be, of course, free. So now I come back to my talk. So here, very often in the talk, I will speak about assets. And that word will be repeated often. And as a matter of fact, for me, assets will be either stocks or bonds. They can be more generally, for instance, commodities such as metals, natural gas, oil. But for this talk, we'll think about them as either being stocks or being bonds. Stocks, that means shares of a company. So in financial mathematics, typically we have two very big groups of models. So one of them is models in which the prices of basic assets are exogenously modeled. That is an input for the model. And the other big group of models is models in which the prices of assets are obtained as a result of the model. In other words, they're endogenous, and they're obtained as some form of an equilibrium between the agents. And what is modeled is the behavior of the agents. So the prices are at the output and the input is somehow the behavior of the agents. So here in this talk, I will focus only on the first group, where assets are exogenously modeled by some stochastic processes. And so here within this very big group of financial models, I will distinguish 4 types. So linear complete, linear incomplete, non-linear and complete, and non-linear and incomplete. And of course, from a mathematical point of view, all the non-linear models will include the linear models in them as a particular case. But historically, research has been developed in this manner, right? Starting from the linear case and going towards the non-linear case. So I have chosen that historical presentation here in the talk. So in all of the talk, we will be given a capital T, a fixed terminal horizon. That's just a positive number, let's say 1 year from now, 2 years from now, etc. And we will be given an underlying probability space. So omega can be a very abstract. I was just wondering whether you can see here some sort of a small, like a hand which goes on the screen. Could you see that?
Yes.
Yeah, all right. So omega can be a very abstract space, right? And not necessarily a space, it can be a very abstract set. Then F is a sigma algebra and P is a probability. And what is very important is that we are also given a filtration. So FT, models the information which is available at time t. So here the index t will always be interpreted as time instant. And so FT is a sigma algebra for each time instant t. And moreover, we have the property that Fs is included in Ft when S is before t. In other words, past information somehow is included in future information. Information does not diminish through time. So I just mentioned, forgot to say at the beginning that if you have some question, you're perfectly free to interrupt me to speak up. I will not be able to monitor the chat because I have plenty of things which appear on my screen. So if you have a question, just interrupt me and ask your question, please. So that is about the filtration. So filtration models the flow of information through time. So and F0, that is the sigma algebra corresponding to the information available at time 0, is supposed to be a trivial sigma algebra. So now, how about the assets? So the assets are modeled through their prices. So I will identify the asset with its price, as a matter of fact. And as I mentioned, the prices are modeled through stochastic processes. So here we will have typically D assets. ST1 will denote the price of asset 1 at time t, ST2 the price of asset 2 at time t, etc., up to STD the price of asset number D at time t. And the typical modeling assumption is that those asset prices are stochastic processes which are adapted to the given filtration. In other words, for every time instant, for each asset I, for each time instant t, STI is a random variable which is measurable with respect to the sigma algebra Ft. We know at each time instant t, we know the past prices and the current prices, but we do not necessarily know the future prices. So now, classically, the price process of each asset is modeled by a semi-martingale. So that is very classical. Nowadays, there are also more general models which go beyond the semi-martingale framework. But here in the talk, we are in the semi-martingale framework. So semi-martingales of this form, where S0I is the initial condition, which is given, the price of each of the assets is given, we can look at it in the market. And then we have an integral with respect to ds, and also stochastic integrals with respect to m1, etc., up to mk, where m1, m2, etc., up to mk are given martingales. And as I said, S0I are the given initial condition. So there is some vocabulary attached to that. If in asset I, in the modeling of asset I, we do not have any stochastic part, in other words, if those here are 0, the dots here are 0, and if we have only a part in ds, we say that the asset is riskless. And if otherwise, if there is some stochastic part, non-zero stochastic part, we say that the corresponding asset is a risky asset. And those martingales, M1, etc., up to MK, we call them driving martingales. Typically, the filtration, as a matter of fact, is generated, right? It's the natural filtration of those martingales, M1 to MK. And moreover, in the market model, there might be some additional constraints, also known as imperfections. For instance, typical constraints are that agents are, for instance, not allowed to short sell some of the assets, but only to buy it. That can be an example of constraints. And now I will give you 4 concrete examples, and I will focus throughout the talk on those 4 concrete examples. So the first example is very classical. So it's the so-called Black-Scholes model from the 70s. So here we have the underlying probability space, and it is endowed with a one-dimensional Brownian motion W. And the filtration Ft, so this W is given, and so the filtration generated by this W is also given, right? So that is the smallest filtration which makes W adapted. That is the natural filtration of W. And here we have D equals to 2. We have just two basic assets. One of them is risk-free. I denote its price by BT. And the other one is risky. I denote its price by ST, right? BT is modeled in this manner, where R is interpreted as being the interest rate, right? If, as a matter of fact, if R is just a deterministic function of time, BT will also be just a deterministic function of time, right, of the form of exponential, exponential of 0 to t RSDS, right? So, so that is the dynamics of the riskless asset, and the risky asset, as I mentioned, it has t, and it is modeled in this manner. So it is risky because here I have a non-zero stochastic part, right? And this one is riskless because I don't have such a stochastic integral here. And so for the those integrals to be well defined, I assume the processes sigma t, RT, and mu t to be predictable and bounded with the process sigma positive. So those are sigma t, RT, mu t, and the price at time 0 of the risky asset. Those are given, right? Those are parameters of this model. And we will see later on that this model is linear and it is also complete. So in example 2 now, I just make a small modification in the previous example. So the modification is the following one. Now I assume in this second example then that I can lend money at the interest rate RT, but I can borrow money at some different interest rate, capital RT, and capital RT is greater than or equal to the small rt. How to make that enter into the general framework that I explained before? So I will assume that I have one risk-free asset B1, which has the same dynamics as before, another risk-free asset B2, which has a similar dynamics, but now in place of the interest rate small r, I put the borrowing interest rate capital R. And moreover, I have those additional constraints on the risk-free assets. The risk-free asset B1, I can only buy it. That's my constraint, but I'm not allowed to short sell it. And the asset B2, I'm only allowed to sell it, but short sell it, but I'm not allowed to buy it. That's my additional constraint. And the risky asset is the same as for the basic classical Black-Scholes model from example 1. So this model, we will see that it is also complete, as in the first example, but now it is non-linear. We will see that. Now I have my third example. Again, I take my basic classical Black-Scholes model and I modify it in the following manner. I allow the risky asset to have a default, right? How do I model that? So as before, I have the underlying probability space, the one-dimensional Brownian motion W. And now I have a random variable var theta, right? Here, random variable theta, which is non-negative and which models the default time, the time of default. So I define here this process n, which is defined as being 0 before the time of default and 1 at the time of default and after the time of default. So it tells me it's 0 if there hasn't been default up to now, and it's 1 if there is default, there has been default. And the filtration will be the filtration generated by the Brownian motion and this jump process n. So in general, the process n is not a martingale, and in the beginning of the lecture, I said that we want our risky assets to be driven by martingales. So how to make the process n a martingale? So I have to subtract something from it. And so that is the so-called predictable compensator. Sorry, that's the so-called predictable compensator. And here I assume that the predictable compensator is of this form, where lambda t is just some given positive process, right? Bounded, which is known as the intensity of default. So, all right, Now, n tilde is a martingale in FT. So I have to assume to make also an additional assumption, which is that W is also a martingale in FT. W is a martingale in its own natural filtration, always. But now I have considered this bigger filtration, which is generated by W and also the process N. So I make that very classical assumption here, right, which is the so-called immersion property assumption. That's an assumption. So I assume that W, which is the Brownian motion in its own filtration, remains the Brownian motion in the filtration FT, which is generated by itself and by N. So now both those W and N tilde are martingales in the FT filtration, and I will consider a risky asset in this form. So as a matter of fact, this risky asset has only one jump, and it jumps at the time of default. So it is driven by the Brownian motion W and by the default martingale N tilde. And for the risk-free asset, I have the same dynamics as in the basic BS model, Black-Scholes model. So for this market model, we will see that it is linear and it is incomplete. Why it is incomplete? Intuitively, because I have two sources of randomness. So two different martingales here, W and N tilde, but only one risky asset which is available for trading. That is the intuition behind the incompleteness of this market. But we will see this in more detail later on. And now I have example 4, which combines the features that I saw in the previous 2 examples. That is, I have a possible default on the underlying risky asset, and also I have possibly different interest rates for lending, small RT, and for borrowing, capital RT. And when I combine that and put in my modeling framework from the very beginning, so I have this. So 2 risk-free assets with the additional constraint that B1 I can only buy and B2 I can only sell, and the risky asset of this form, as in the previous example, with the 2 driving martingales, W Brownian motion and N tilde default martingale. So for this one, we will see that it is incomplete, as in the previous example, for the same reasons. We have 2 sources of randomness, only 1 risky asset, but it is non-linear, as in the second example. So it is non-linear and it is also incomplete. So let us now come back to the general framework from the beginning. If I want to explain what I mean, precisely what I mean by linear and respectively non-linear market, what I have to do is to explain what is a portfolio, and more precisely, what is known as a self-financing portfolio. So now we speak about portfolios. So X will be the given initial wealth of the agent. And so the agent can choose its trading strategy in the underlying assets. Remember, we had D underlying assets in the general framework. So FT1, FTD is chosen by the agents. So that is, FT1 is the amount of money in asset 1 at time t, etc. FTD is the amount of money at time t in asset number D, right? The amount of money. So that's the money. All right, and those are predictable stochastic processes which are sufficiently integrable. Now, what is the wealth? What is, if I start from small x, right? And if I follow those strategies phi1 up to phi d, so what is my wealth at time t, starting from initial wealth x and following the strategies phi? So it is the sum of those phi ti's, of course, the sum of the amount of money that I have in each of the d assets, right? And V0 is equal to the initially given x. So that's the so-called value of the portfolio at time t, or wealth at time t. And now I consider only portfolio strategies which are self-financing. Is there some question?
Yes, for the expression of the value of the portfolio,
yeah,
there is the variation of the prices are missed, no?
So here is just you know, yeah. So I understand what you mean. Here we have to pay attention to the fact that phi ti's here, phi t1 up to phi td, that's amount of money. That's not a quantity of stock, right? So that's the amount of money, right, which I put in asset 1, and this one, the amount of money which I put in asset D, right? The quantities will be the phi t1. So the quantity in asset 1, that is the number of shares, for instance, in asset 1, if asset 1 are shares, is phi t1 over st1, right? And the quantity in D will be phi td over STD. That will be the quantity, the number of shares. Is it fine?
Thank you. Thank you. Yes.
You're very welcome. Yeah, that's a very good question, especially for those who are accustomed to financial modeling. Sometimes we consider the amount of money and sometimes the number of shares. And of course, there is an easy way to pass from one to the other. And now what is very important is that I consider only portfolios which satisfy the so-called self-financing condition. So in financial mathematics, we always consider only self-financing portfolios. And what are those portfolios? Those are portfolios which satisfy this condition here at the bottom. So let us look here, and I thank you for your question, because let us now first look at this fraction here. What is this fraction? Phi ti over STI minus. So that corresponds exactly to the quantity that I put in asset I at the time instant t minus. So ST minus here stands for the left limit of the process ST at time t, right? ST minus is for the left limit. Why do I take left limit? That I have to take for mathematical reasons, because some of those STIs might have jumps, right? And hence I have to take here some process which is predictable, right, to be able to define the stochastic integral. So phi ti is predictable because I have taken them to be predictable, right? But STI in itself is in general not predictable if it has jumps. So in order to take something which is predictable, I have to take the left limit. So that is for technical reasons, and that I can interpret as the quantity just at the instant t minus, right? And what I say here is that the variation of the value of the process, of the value of the portfolio between time instant t minus and t, if you want, it is due only to differences in the stock prices, right? That is the self-financing condition. Of course, that's a shorthand differential notation. You should understand that in the integral sense, right? All right, so let us see what it gives in the concrete examples. So I think it's up just before that. I just look at the self-financing condition again. So this self-financing condition, I wrote it in the more meaningful integral form. It becomes this, right? And now you remember that the stock prices, they were modeled by semi-martingales of this form. So I can replace DSTI by its model here in the self-financing condition. And if I do that, I obtain something of this form. So the value of the self-financing portfolio at time t is the initial value plus something in ds and plus something in some stochastic integrals, right? Very good. So the thing which appears in the ds, right, in front of the ds, I call the driver. And now the vocabulary is the following. If this driver, which I see in the self-financing condition, right, after replacing the model for SI, if this driver is something which is linear in the value of the portfolio and also linear in each of the strategies, we speak of linear financial market model. Otherwise, if there is some non-linearity, we speak of non-linear model. That is, I write in each model, I write at the self-financing condition, I replace the model for the stock prices and the bonds, and the driver that I see appearing in front of the DS, if it's linear, the model is linear. If it's non-linear, the model is non-linear. So let us see in the concrete example, Black-Scholes model. So that was Black-Scholes model with the two basic assets, riskless and risky. So I want to write the self-financing condition for the value of a self-financing portfolio. So here phi t will be the amount invested in the risky asset at time t. And of course, Vt minus phi t will be the amount which remains and which will be invested, of course, in the other asset, because there are only two, that is the riskless asset. So Vt, the amount of money in the risky, Vt minus Vt in the riskless. And then I write the self-financing condition. It's very simple. It has just two summands, right? It's this one, dst, plus this one, dbt. So here, whether I put st minus here, bt minus here, it doesn't matter very much, because here those are continuous processes, continuous in time, both st and bt. So I will obtain the same integral. So whether I put st minus or just st, I have the same stochastic integral, and whether I put bt minus or bt, I have the same stochastic integral, because as a matter of fact, st and bt are continuous. Very good. So I replace st and bt by the models, And finally, I obtain that the self-financing condition is of this form. So here is the driver, and obviously that is something which is linear in Phi and in Vt. Remember, Rt, μt, and Rt are given, right? So Rt and μt are given. So that's linear in Phi and linear in Vt. So that's a linear driver and a linear model. Now, let us see in the second example where I had two different interest rates for borrowing and lending. So how do I model the constraints here? So Vt is the amount invested in the risk asset as before. Then what remains to be invested in the two riskless assets is this amount of money, Vt minus Phi. And so how do I model the constraints? So if this is positive, I put it in asset B1. If this amount of money is negative, the opposite of it, that is minus Vt minus Phi, will be the amount which I get from selling in the asset B2. Right? So if I write the self-financing condition, that is exactly what I will write here. And I replace then DST by its expression, DBT1 by its expression, and DBT2 by its expression. Its expression in term, I mean, its model. And so I do some elementary computations and I get this, right? So in this second example with the two different interest rates, I have obtained this driver, and that is obviously something which is nonlinear in Vt, and also it happens to be nonlinear also in the strategy in the Phi t. So that's nonlinear model. Let us see example 3. Example 3 was the model with the default on the underlying risky asset, right, on the risky asset, and just one risk-free asset. So if I write the self-financing condition, you will see that we obtain this. So here now I have the two driving martingales, the Wt and the default martingale and tilde, but the driver is the same as in the classical Black-Scholes model. The difference is here in those stochastic integrals, but the driver in itself is linear and the same as in the classical BS. So that's a linear model, but it will turn out to be a linear incomplete model, and that will be the main difference with the classical BS. In example 4 was combining different interest rates and default on the risky asset. If I write the self-financing condition, I obtain this, and here I have a typo. So here that should be a small parenthesis. So it's Vt minus Phi t plus positive part, right? So all this in the big parenthesis is the driver. So it's a nonlinear driver. It's the same driver as in example 2. The difference is here that I have those two driving martingales. So this is a nonlinear model, and it will turn out to be nonlinear incomplete, right? So now linear, nonlinear, we understood that is really according to the driver, which appears in the self-financing condition. Now, how about complete and incomplete? So that is related to the notion of European option and the notion of replication of a European option, and I will introduce that now. So what is a European option? Now, that is not a basic asset. That is some financial contract, right, which I put on the basic asset. It has two counterparties. The jargon is buyer and the seller. Let's say the seller is Dr. Jarrett and I'm the buyer. So we will enter into the contract today. Let's say today is the time small t. And at the terminal time capital T, Dr. Jarrett will give me the specified random variable psi, which is f capital T measurable. So a European option is just modeled by its terminal payoff at the terminal time capital T. That is what Dr. Jarrett will give me at time capital T, and that is a nef capital T measurable random variable. So each capital Ft measurable random variable, you can call it a European option. And now what is the aim of Dr. Jarrett, who is the seller of this option? Well, he wants to find the smallest initial capital small x, which allows him to build a self-financing portfolio strategy phi, such that his terminal wealth, right, the V capital T, following this strategy phi, is greater than or equal to the terminal payoff that he has to give me. Formally, so the super hedging price of the European option that Dr. Jarrett wants to determine, because he's the seller, is the smallest initial capital, such that there exists a self-financing portfolio phi with this property. So if Dr. Jarrett manages to find that and to sell me the option for this P0, then he will be able to build a portfolio such that at the terminal time, he's super hedged, whatever happens in the world. Now, if there exists some initial wealth X bar and some strategy phi bar such that I have exactly the equality, that is the terminal wealth matches exactly the given payoff psi, then I say that I'm perfectly hedged. More precisely, Dr. Jarrett is perfectly hedged. If such X bar, phi bar exists, he's perfectly hedged. And the price of the option is this X bar, right? We say that the option is this case, we say that the option is replicable or perfectly hedgeable, and its price, no, not super hedging price, but its price is this X bar, this initial wealth, which allows to achieve this matching, right? I think that is clear. So in other words, to determine whether a given European option with payoff psi is replicable, what I have to find, or more precisely what Dr. Jarrett has to find, is if there exists an adapted process VT, which will correspond to the wealth process, and trading strategies phi T1, etc., up to phi TD minus 1, such that the self-financing condition is satisfied, and moreover, this terminal condition is satisfied, that is V capital T is equal to the given psi. So if we manage to find such VT phi 1 phi D minus 1, which achieve that, then psi is replicable, right? And this is its replicating strategy. If you do not manage to find that, then it is not replicable, and I have to be interested in super hedging. In the concrete examples, how much time do I have? So, sorry. So I still have some time. So let us look at the concrete example. The BS model, the classical BS model, right? So I have to be a little bit more concrete because I have to specify in which space, I mean, the integrability assumption on the psi. So I was a little bit vague in the general part. I said psi is F capital T measurable, satisfying some integrability assumption. So here in the concrete examples, I have to be more concrete. So I take it a square integrable, ft measurable and square integrable. And I will consider only strategies which are in the space H2. And in the space H2 is just the L2 space, right? Where I integrate with respect to the product measure dp cross dt. So now my question is this given psi replicable? So in other words, I have to figure out, or more precisely, Dr. Jarrett has to figure out if there exists a pair of processes, Vt phi t, right, such that the self-financing condition is satisfied. That was the self-financing condition in this model. And moreover, the terminal condition is satisfied. V capital T has to be equal to the given psi, right? It is usual that this equation, right, with a terminal condition, it is usual to write it in this manner, right? That is very common. So how do I obtain this equivalent expression? Just by integrating here from small t up to capital T and using that V capital T is psi. If I do that, I obtain this equivalent expression, and that has to be satisfied for all t's between 0 and capital T. Here is now the terminal condition. Well, an equation of this form is called a backward stochastic differential equation, right? Obviously, it's a differential equation. Obviously, it's stochastic. And why is it backward? Backward because I have fixed not the initial condition, but the terminal condition, the condition at time t. And what I want to find is what is the V0, and more generally, what is the Vt, and what is the phi t, right? I give myself psi. I want to find Vt and phi t. So this backward SD in this example is in a Brownian filtration, because here the filtration was the filtration of the Brownian motion. It has a linear driver, because that is what popped up from the self-financing condition. And the driver is of this form. Please notice here the minus, right? The minus with respect to before. So usually BSDs are given in this form, and so the driver is this one with the minus sign. But of course, that doesn't change whether I take the minus or not. That doesn't change the fact whether it is linear or not, right? Okay, so in the second example, again, in the second financial model, Dr. Jarrett tries again to sell me an option psi, which is ft measurable and in L2. And now he wants to find a pair of processes Vt phi t, which satisfy this, right? Again, same terminal condition. Now this appears, right? That was the driver that we had from the self-financing condition in the second example. The equivalent form of writing that is this. And so this is a BSD, again in a Brownian filtration, because in this second example, we are in the Brownian filtration. That's the example where we only have different rates for borrowing and lending, but nothing else. And the driver is nonlinear. It is of this form with the minus that I have copied from here. Let us see the third example. So before seeing the third example, let us first look at those first two. So Dr. Jarrett wants to find this pair VT phi t. So can he find it? In other words, where does this BSD and the previous one have a unique solution? And the answer is yes, it has a unique solution, and that is given by the classical theory on BSDs. So the very classical result in Brownian filtration, square integrable data, and the driver F, which is Lipschitz. So I know that their existence and uniqueness of the solution of the BSD. In other words, there exists such pair of processes, and the existence and uniqueness is in this space. So what does it mean? It means that psi is perfectly hedgeable in both examples, in this classical BS and in the Black-Scholes model with different interest rates. And the price of the option, the price that Dr. Jarrett will want me to pay today for this option, will be the value at time 0 of his replicating strategy. And that's, of course, the solution at time 0 of the BSD with driver F and terminal time, the payoff of the option, right? In those two examples, we found that any European option psi is perfectly hedgeable or replicable, and the jargon and the vocabulary is that this market is complete. Any European option can be perfectly replicated. The market is complete, both from example 1 and example 2. So those are both examples of complete markets. The main difference was that in the classical Black-Scholes, the driver was linear, and in the second example, the driver was non-linear. So in the case where the driver is linear, I denote that F lin for linear, we have an explicit closed form solution of the BSD, of the solution of the BSD. And this explicit form of the solution is this one. It's just the form of the expectation under P of some random variable gamma t times psi. And this gamma t depends only on the given parameters mu, sigma, and r. So it is very common. So that's an explicit form of the solution in the linear complete case. And it is very common to make a change of measure here and to write that in this manner, where Q is a measure equivalent to P, and the density of Q with respect to P depends only on that mu sigma, on mu and sigma and R. Okay, in the complete nonlinear case, that was example 2, that all European options are replicable. The BSD has a unique solution, but I do not have an explicit formula for the solution, and I have to look for numerical methods, right, to solve the BSD and to determine. Dr. Jarrett has to solve numerically the BSD so that to determine how much I should pay him today for the option. And now let us look at example 3 and 4. As a matter of fact, in example 3 and 4, and that's the main difference in that group of examples from the previous ones, the market model is incomplete. Indeed, if I take some option psi, Dr. Jarrett takes and wants to sell it to me. So he has to find out VT and phi t, solving this BSD, right? So in the third example, the driver is linear. In the fourth example, it is non-linear. But basically, that is the BSD that Dr. Jarrett has to solve. And here you see I have two sources of randomness, but only one control, phi t, which is the same in front of the two. Sigma t and bt are given, remember. So two different sources of randomness, but only one somehow control process, phi t. So in general, such a BSD doesn't have a solution. Maybe for some very particular payoffs it has, but for there are payoffs in L2 for which it doesn't have a solution. So, and hence, this market model from example 3 and 4, where we had the default on the underlying asset, it is incomplete. It is incomplete. So still, I can say something about the super hedging price. So Dr. Jarrett we'll have to look to super hedging, not exact hedging, not perfect hedging, but super hedging. So, and the super hedging price, we can show this theorem, right? The super hedging price, P0, is equal to this. So that is a dual formula for the super hedging price of the European option with payoff psi, right? Such type of equalities are known in financial mathematics as pricing hedging duality. So what does it say basically? So remember, I do not have the solution to my initial BSD of the model, right, under P. So what I'm going to do, I'm going to intuitively, I'm going to build some auxiliary models, right? Some auxiliary models, which will be, those auxiliary models are indexed by those measures Q, right? And each of those auxiliary models is complete. So I take the same driver as in my original model, but now I artificially, in the auxiliary models, I allow the agent to be able to hedge the Brownian motion, if you want, but also to be able to hedge against the default. So here, artificially, I allow him to have a trading strategy in the auxiliary model, not in the initial one, in the auxiliary model to have a trading strategy phi t and also KT. So the trading strategy has two components, right? So now this BSD under Q in the auxiliary model number Q, so it has a unique solution triplet VT, phi t, KT. So this makes sense, right? And I can show that the price of the super hedging price in the original model is equal to the supremum of the prices in those auxiliary models, the supremum over all the Qs of the prices in those auxiliary models. Now, what is the difference between example 3 and 4? The only difference is that in example 3, that driver F is linear, that is F-lin. And in example 4, the driver is non-linear, right? But in both examples, I have this formula. I have just to put the right driver for each of the models. I also have one more result, and I will display this result, and that's the final result. So remember, the super hedging price in examples 3 and 4 does not solve a BSD. We said that, does not solve a BSD, because the BSD, as a matter of fact, when we wrote it, in the original model, in the original models 3 and 4, it might not have a solution. But what we can show is that it is the minimal super solution of a BSD with constraints. So I will not display the constraints. So those are constraints on the trading strategies. I will not display them, and I will refer you to the two papers. So the last two results, the last two theorems that I displayed, they come from this first paper, which is already published. And so they refer to those nonlinear incomplete markets of example 4. And we have also a sequel of those results, which is in this second paper, and it is about the so-called American options. So I don't have time to speak about that, but you can have a look and see what type of pricing hedging dualities we have for American options, and also what type of characterization in terms of minimal super solution. Now for American option, it will be constrained reflected BSD. So just a final remark and I stop. So please let us be careful. So here for this result, so when the driver F is linear, so this functional is a linear functional of psi, right? That operator, which takes a payoff, right, and returns the solution. When the driver F is linear, it is a linear functional of psi. When the driver F is nonlinear, this is typically a nonlinear functional of the payoff psi. If the driver is convex, typically that is a convex functional of psi, and that was the case in example 4. But in the paper, as a matter of fact, we can do that for drivers which are Lipschitz, but not necessarily convex. And so we do not, the proof of those results of those theorems is not based on convexity arguments, because in general, that is some non-linear functional of psi, which is in general also non-convex in psi. It can be convex if F is convex, but if F is not convex, it will in general be non-linear and non-convex in psi. So Let me mention that in those papers, because I saw that Professor Ruknin is attending, so we use some of our earlier results, which are based on joint works with Professor Ruknin, Professor Marie-Claire Kenez, and Professor Imkala. And so I will stop here and open the floor for discussion. Thanks very much.